Hello everyone. I would like to welcome you all to our session. My name is Dr. Amirhossein Hosseinmemar, and I'm here to present push recovery and active balancing for inexpensive humanoid robots using reinforcement learning and deep reinforcement learning. The number of our paper is 41. Here's the outline for today's talk, and let's start with introduction and motivation. Moving robots from factory floors to the everyday lives of humans is a challenging task. Traditional wheel robots are more stable and balanced than humanoid robots. Humanoid robots are closer to a human's body shape, and as a result, they can potentially function better in a human environment. If a robot has a collision with an object, an external force will be applied to a robot, which typically causes the robot to fall. Falls are a common cause of injury in humans and similarly can be very damaging to humanoid robots. Here's an example of industrial robots working environment, and as you can see in these pictures, the robots are kind of fixed in an environment and they cannot be really portable and do different tasks. And in here we have examples of humanoid robots working environment. On the left side we have an uneven terrain that a robot could walk on it, and on the right side we have another robot which is Atlas that is walking on turf. Push recovery and active balancing for an expensive humanoid robot is actually something that we are focused on. I would like to emphasize that the inexpensive term in here is very important for us. What do we mean by inexpensive humanoid robots? This means that we do not actually rely on, or to be more precise, the robot does not rely on very expensive hardware. So it uses inexpensive servo motors that break easily, an expensive battery as a source of power, an expensive sensor to communicate with the outside environment, an expensive CPU as a computational power, and as an expensive custom body frame as a robot's skeleton. So for this research, we have come with 3 questions. The first question is our closed loop control going to be fast enough for an expensive robot that are equipped with cheaper hardware for responding to an external push on time? Second question, are any of our reinforcement learning and deep reinforcement learning push recovery techniques going to be able to replace the parameters that a human operator provides for recovery based on his or her experiences? So basically we want to know if a robot can have a better experience than a human. Question 3, which of the proposed approaches, reinforcement learning or deep reinforcement learning, results in a better recovery if the surface directions and impacts are unknown to the robot? For example, the robot does not have any sort of a prior knowledge. Now let's talk about some backgrounds and related work. Toyoda's running robot was a very good robot that could actually recover from external pushes. One of the main problem with this robot was it was very expensive. HRP2 could recover its walk-in and balance from different pushes in various directions. It was very costly in terms of generating the trajectories of robots. So every trajectory almost takes 1 second to generate, and this is not fast enough, and it causes a robot from time to time to fall. Mabel in 2011 mounted on a boom of radius of 2.25 meters that could walk around a fixed circle and it was being hit by external pushes. However, again, it was mounted on a boom, and something was holding it from the inside. The other robot, which is Atlas, is very famous, is a hydraulically actuated robot. This robot has a high voltage three-phase power supply for the actuators. The reaction time of Atlas is very fast since it uses a fiber optic line with a rate of 10 gigabit per second for transmitting the instructions. And one of the main issues with this robot is that it is extremely expensive. Gu et al. In 2017 investigated deep reinforcement learning and Q-learning in one particular setup in both simulation and the real world. They used robotic arms with 7 motors, and it was a fixed arm, no change in the environment, and it was not able to do many of the given tasks in the real world. So it could do some work in the simulation, but when you take it to the real world, it wasn't really functioning properly. Kumar et al. In 2018 investigated a walk-in mechanism for a 2D simulated bipole robot without the upper body with 6 degrees of freedom, which means 6 motors, fixed environment and no upper body, and it was applied only in the simulation. So the solution wasn't applied to the real world. Gill et al. In 2019 studied reinforcement learning and Q-learning for teaching a simulated now humanoid robot how to stand up and walk a short distance in a straight line. So the problem with this was the environment was fixed, means there were no differences in environment, and everything in the environment was known to the robot. It was also in a simulation. High performance GPU requires to compute all the trajectories, so it was very costly. Now let's have a look at some active balancing and push recovery balancing strategies for a humanoid robot. There are 3 common strategies for the push recovery. First off is center of pressure, or COP. This approach usually is used on controlling ankle on both feet, and it is also known as ankle strategy. It's suitable for external live pushes. Centroidal moment pivot, CMP. This approach is usually based on controlling ankles on both feet and hip, and it is also known as hip strategy. CMP can be used for small and medium disturbances and is thus an improvement over COP. And last but not least, stepping. Stepping can handle small, medium, and large disturbances in many cases. This involves taking another step to relocate the center of mass within the supportive polygon area. Now let's have a look at the design and implementation of our robot. Our robot is called Polaris, and his height is 95 centimeter with a weight of 6.9 kilogram. It has 20 servo motors, 12 of which are on both legs, 6 of them on both arms, and 2 of them on the neck. For Polaris, we have a parameterized walking engine that has 9 main parameters that are step X, step Y, step height, X offset, Y offset, Z offset, step pace, hip pitch, and ankle pitch. All of these parameters are actually very important to a robot, and each of them are given a kind of threshold from minimum to maximum that the robot is allowed to take. For example, step X is the amount of distance that the robot can go forward or backward, and you can see that the minimum is -5 centimeter, which is going backward, and +5 centimeter, which is going forward. Step Y, for example, is going to the left and right, and same thing is with the distance is based on centimeter that goes left to right. The step height is how high the step is. For example, we start with 1 centimeter and it goes maximum to 8 centimeter. We have X offset and Y offset, which is for relocating the feet. And it is going to be, for example, we are given offset to go a little bit forward or to go a little bit backward and calculate all the trajectories from that point instead of the very center of the body. Z offset is the height of the robot, that it goes from minimum 34 centimeter to 44 centimeter. So 34 centimeter means it lean more on the knees. Then we have a step pace, that it goes how fast actually the robot can finish a cycle. And we have hip pitch, that it's talking about the tilt of the robot for the hip that goes back and forth. For example, it wants to lean forward or it lean backward. For ankle pitch, it's also the same tilt, but it's on both ankles. And the measurement unit for these two are degrees. For the loop controls, we have open loop control and closed loop control. The main difference between the open loop control is that there is no feedback in here. So we send a position to a robot and we do not check if it went to that position or not. The closed loop control feedback is we send the robot to a position, then we check, we measure the errors, and the robot actually tries to fix that error. The IMU, linear velocity discretization. So we have discretized the accelerometer for this robot. And we say that, for example, from 0 to 0.2, that is a sensor noise, and it is shown with a green color. Then we have from 0.2 to 0.9, that is the acceleration for the light push. And we have 0.9 to 1.2, that is acceleration for medium push, and 1.2 to 1.4 is the acceleration for the hard push. This means that if we receive a push and it was in any of these discretized states, we can identify that how's the measure, and based on that the robot can actually take an action. Then discretization of the robot states. We push the robot from 4 directions: left, front, back, right. And the push strength is going to be light, medium, and strong. At the end, what we have is the robot going to be either on a stable robot or a fall state. So we have 4 multiplied 3. It's going to be a total of 12 discretized states. For the reinforcement learning, we use Q-learning. For each model, for example, out of that 12 model that we just talked about, we have, for example, for front 40 centimeter, because we have 30 centimeter distance, 40 centimeter distance, and 50 centimeter distance for every direction. So let's say for front 40 centimeter, the model was constructed with a lookup table. We use Python version 2.7 and NumPy 2 multi-dimensional array. So we also use simulation to assess the actions that the robot takes. For deep reinforcement learning, for the function approximator, we use a feed-forward a neural network, and the framework that we used was TensorFlow, and along with Python and Ubuntu Linux 16.4. Here is an overview of our network. As you can see on the left side, that we are showing it with input 1 to 9. These input 1 to 9 are actually referring to the robot's walking engine that I talked about earlier. And what we have in here, we have 20 hidden layers, but because of the space limitation in here, we just demonstrate 5 of them. So 20 hidden layers, and at the end we have a reward that it's going to give a reward to that particular action that the robot take. And based on that, the robot tried to fix its next step. So for the deep neural network, we use sigmoid activation function to keep the output of the deep neural network between 0 and 1. We also use binary cross entropy to measure the performance of our deep neural network. For testing our evaluation, experimental environment were done in two worlds, one real world, the other one simulation. Our approaches were reinforcement learning and deep reinforcement learning versus baselines. The baselines were using open loop control feedback in the real work and simulation, and closed loop control, which was taking random actions only in simulation. The main reason that it was only in simulation was that we did not want to harm the servo motors in the real world. So we have adapted the experimental environment from RoboCop Push Recovery Challenge from 2018, and you can see that the robot is doing the walk, and a bottle of water with the weight of 2 liter is released from a distance which is minimum 30 centimeter, and then the robot needs to balance itself, and the robot does not know actually where and when the push is coming from. For the real world, we have 12 discretized states and 3 pushes for every states, and we have 3 environments, which are concrete, carpet, and turf, artificial turf. And we have 2 machine learning approaches, RL and deep reinforcement learning, and we have 1 base case which was using the open loop control. In total, we have applied 324 pushes to the robot in the real world. Here's an example of hitting the robot from the left side of the robot with a 2 liter bottle, and the robot absorbed the push and it recovers successfully. The average success rate for this on concrete in the real world was, for the base case, 53%, for reinforcement learning 81%, and deep reinforcement learning 86%. We do the same thing for the robot walking on the carpet, and the robot again had different actions and reactions. So for the base case, the robot covered 39% for RL, 58%, and deep reinforcement learning, 61% of average success rate. Then we tested the robot on artificial turf, which was very soft and very thick. So the recovery was harder in here, and the average success rate for the base case was 19%, for deep reinforcement learning 42%, and for reinforcement learning 47%. So we did the same thing for simulation, but since simulation we didn't have problems for servo motors, braking servo motors, instead of 3 pushes we had 30 pushes, and instead of 3 environments we had only 2 environments, which were concrete and artificial turf. And we had 2 machine learning approaches and 2 base cases, so the robot could take actually different random actions. So overall, we applied 2,880 pushes to the robot. Here's an example of hitting the robot from the right side in the environment of simulation, and the robot can actually recover successfully. So average success rate on the concrete for the base case, the average of the base cases was 11%, for RL 84%, and for deep reinforcement learning 92%. And here is another recovery on artificial turf, that the robot is being hit and recovered successfully. So for this one, you can see that the recovery is also lower than the previous one, because the turf is harder to recover. So the base case 7%, and then we have RL 80% and DRL, which is our deep reinforcement learning, 92%. So for the conclusion, we want to first answer the research questions that we brought up at the very beginning. The results show that Polaris can successfully recover from different pushes with various impacts, including strong pushes as well as pushes from different directions. As a result, show both reinforcement learning and deep reinforcement learning performed well, and they can be replaced to human knowledge. In the real world, RL achieved 62% overall recovery rate, while deep reinforcement learning achieved 63%. In simulation, RL achieved 81.5% overall recovery success rate, while DRL achieved 92%. In the real world and simulation, RL achieved 69.8% recovery success rate, while DRL achieved 74.6%. In all the categories, DRL performed better in comparison to RL. Our contribution for this paper, a novel approach to push recovery based on learning appropriate step responses using RL and DRL for inexpensive humanoid robots, a 3D model of Polaris for testing and training purposes, and the simulation, a novel way of using RL and stepping for push recovery using inexpensive hardware, a novel approach in deep reinforcement learning that learns how good or bad a chosen action is using inexpensive hardware. Some of the feature research that we could have in here, including the direction of the walking gait, forward and backward, and simplify it by using symmetry between the left and right side of the robot. These two addition features might reduce the learning process, use the newly trained RL component to generate a larger data set for training the deep neural network, and possibly improve performance further. Have a deep neural network that outputs walking engine parameters. Investigate other approaches of neural network for our framework, such as using a long short-term memory neural network. Replace the lookup table with a deep neural network. Start the learning process with smaller ranges. Increase the step height range from 1 centimeter to 8 centimeter to 5 centimeter to 8 centimeter. And here are the references. Thank you very much all for listening to my talk, and I greatly appreciate that. Bye.